Nice to meet you. Nice to meet you. Appreciate it. Oh, great. Awesome. Thank you. I don't know, but I'm Tom in Hashgraph. Very sure. Nice to meet you. Oh, you got your
Want me?
I can stand there. I can present it.
You're good.
Hello, my name is Andre Kim, and I'm from Blockchain Eye. Thanks for coming here, and thanks for coming here too. Yeah. Please let me introduce. I'm Andrew from DNA Fund. Please welcome.
Hey everyone, thank you so much for coming to this event tonight. We really appreciate it. My name's Andrew Lee. I'm a partner at DNA Fund. DNA Fund is Brock Pierce's fund, blockchain fund. Brock Pierce is the founder of EOS. He's the chairman of the Bitcoin Foundation, and he's also the founder of Blockchain Capital. We're really happy to have everyone here tonight. We're one of the supporters of Hashgraph that have been coordinating their Asia tour for the past 10 days. We were just in Hong Kong and Singapore right before that. And the level of interest has been very high. All of the previous meetups were blowout successes, and everyone really seemed to enjoy it, and we're really engaged with Hashgraph. So it's really my great honor to be part of this amazing team, and happy to answer any questions and be a point of contact afterwards. And I'll pass it on to Edgar, head of Asia for Hashgraph.
Thank you everyone for coming on a Sunday evening. I'd like to start by thanking Blockchain Eye and DNA Fund for putting this meetup together. So just to introduce myself, my name is Edgar Sia. I grew up in Singapore, went to Carnegie Mellon for my undergrad. I worked at Merrill Lynch for 7 years after that, 2 years in New York and 5 years in Tokyo. So I ran the asset-backed securities business for Bank of America Merrill Lynch across all of Asia. I left finance in 2010. Did nonprofit work in West Africa for a few years. And since 2012, I've been an early stage investor and advisor to tech companies. And I've been looking at blockchain companies for the last 1 to 2 years. Very excited about blockchain technology, but also saw a lot of the limitations of existing technologies. So when I was introduced to Swirls and to Hashgraph about 7 months ago, I saw this tremendous technology that I feel can really transform the world and eliminates all the limitations of prior technologies. And I got so excited about their technology as well as the team. You know, Mance Harmon and Dr. Lehman Baird are two of the most capable and humble people that I've ever come across. And so I really, wanted to join them and be a part of it. So I joined the company about 5 months ago. And I run the Asia Pacific region for the company. So next, I'd like to hand over to Tom Trowbridge, who's the president of Hedera Hashgraph.
Thank you, Edgar, and thank you all for coming. Tom Trowbridge, I'm president of Hedera Hashgraph, which is the public ledger version of what we're doing in the public ledger expression of the Hashgraph algorithm. Quick background on me, I went to Yale for undergrad, then did investment banking, Columbia Business School, even though Columbia Business School alum here as well, which I just found out, which is great. And I started investing in technology as part of a private equity fund in 1998. And subsequent to that, kept investing on the personal side as I worked at Goldman Sachs, among other financial institutions, particularly hedge funds. I came across Swirls and this team by way of investment, and I actually invested in Swirls, which is how I found the company. And after I invested, I got to know Dr. Lehman Baird and Mance and the team over time, and was more and more impressed with them. And I think the interesting thing is that the more you know about technology, the more excited you get about this. And the more you know about blockchain, the more excited you get about this. And that is something that's very rare in this industry, where you get to know something, and the more you learn about it, the more you start to be a little unsure if the pieces all fit together in some of the projects, but here is the reverse happens. So I just want to make that point. I joined to help build out the governance council, and then have taken on other responsibilities over time. But I'm thrilled to be here. Quickly on Dr. Lehman, Merritt, and Mance, background on them. Lehman got the fastest PhD, we think, in Carnegie Mellon history. He hates it when I say that, but it was 2 years and 9 months. So for those of you who have PhDs, it's pretty fast. And I'm going to leave Mance to give you his background in particular, because it's a pretty unique piece of it that's relevant, I think. They started working together. They met in August of 1993 and have been working together ever since. They've had multiple startups, multiple successful businesses they founded together. And I think it's pretty rare to find two founders who've done multiple successes and worked together for 25 years. And that gives a testament to the type of people they are, and the integrity that they bring to all the projects they work on. So with that, I'd like to introduce Mance Harmon, CEO of HashGraph.
Thank you. Well, thank you all for being here. It's my first time to Korea, and I'm honored that you're here to be here and share this with me tonight. As Tom mentioned, Lehman and I have been working together since 1993. We met working for the U.S. Air Force Senior Scientist for Machine Intelligence, doing machine learning research back in the early 90s. We then both went to teach at U.S. Air Force Academy, computer science. I was the course director for cybersecurity at the academy. Lehman was a full professor. And then I moved over to run a massive simulator for the Missile Defense Agency for the U.S. government. So I managed the program that built the war game simulator that makes it possible for the U.S. and its allies to figure out how to protect its citizens from incoming nuclear ballistic missiles, and ran that for a while for the government. Lehman and I decided we wanted to be entrepreneurs, so we started our first company in identity, sold it to a Fortune 500. I started as a senior exec for product security for that company. Then we started our second company, again in the space of identity, and sold that to private equity 6 years later. I went to work for a major identity vendor, Ping Identity, as the head of architecture, and I stood up their labs organization. Lehman went to work on this problem in 2012, the problem of distributed consensus at scale, highly performant distributed consensus at scale. He worked on it for years, and in 2015, he had a breakthrough, and today we call that the hash graph. And we decided at that time to start our third company, and it's Swirls. So with that, I'm going to dive in to the technology. If there are questions, by all means, feel free to ask them, and I'll give you the detail about what we're doing here. So what is HashGraph? To start, it's not blockchain, obviously. It's an alternative to blockchain. It's fundamentally different. It's mathematically proven. So in everything that we do, we first start with the math. We start from first principles and try to build the best algorithms formally possible. That's why it took Lehman so long to come up with the hash graph. But everything that I'm going to be presenting here today is formally proven. And by the way, the math proofs are in a white paper that are on our website, and they've been there for 2 years now. So this has been in the market for that long. It's also patented. And I get a lot of questions about the patent and how we intend to use it. I'll answer all those questions tonight so that you have some understanding of our strategy. And then it's also implemented in software. So the market is split into two halves. There are the public networks, like Bitcoin and Ethereum and the other emerging platforms, EOS, Tezos, etc. And then the private or permissioned networks, represented by platforms like Hyperledger, Corda, EEA, Coco. The private or permission side of the market doesn't use blockchain at all. it uses this category of distributed consensus. It's called leader-based algorithms. Some of the names of the algorithms are Paxos and Raft, PBFT, RBFT. There are dozens of variants on this category. Conceptually, it's really pretty simple to understand. Each one of these computers here is a computer in the network, a node in the network. And the computers elect a leader. The computers each have a local copy of a database. Most people call it a ledger. I call it a database. I prefer database. But each of these computers have a local copy of a database, and anytime a computer wants to make a change to the database, a transaction, it sends that transaction to the leader. The leader accepts all of the transactions from all of the computers, puts them into an order, and then passes those transactions in that order down to every node in the network. The computers take those transactions and commit them to the database in the same order. This is how the computers, the databases, maintain consistency, how they stay in sync with one another. So what are the problems? Number one, about the maximum throughput in a leader-based system is roughly 1,000 transactions per second. Certainly with Paxos and Raft and PBFT and those, it's about 1,000 transactions per second. Most recently, I've seen reports of 7,000 or 8,000 transactions per second, but not hundreds of thousands or even tens of thousands of transactions per second. Also, it doesn't scale well. So as we continue to add nodes here in the network, the time it takes for this to work, the latency, grows, doesn't scale well. And so most of these types of systems, when they're deployed, they only have a couple of nodes in the network. I'm sorry, a couple dozen nodes in the network. Many of them only deploy with 4 nodes in this network. So they don't really scale well. There are a couple of other problems. By design, each one of these computers knows the IP address of the leader. And so if any single computer is compromised, either from an insider threat, like a disgruntled employee, or malware or virus, and the attacker can send the IP address of the leader to a botnet, then they can direct a distributed denial of service attack against the leader. They can attack the leader with a DDoS attack, effectively bringing down the entire network. And they can do this with almost total anonymity. It's very difficult to figure out which computer has been compromised. Now, what would happen is that the community would quickly realize that the leader is no longer talking, no longer communicating. And so they just simply elect a new leader. They choose a new leader. And that happens within a couple of seconds. However, the problem is that whichever computer here is compromised has to be given the IP address of the new leader. That's the design of the architecture. So all they do is they change the target of the DDoS attack, and they can keep the network down for as long as they can maintain DDoS on the leader. They just follow the leader. So that's a fundamental flaw in the architecture. This is not something that we discovered. This is already well understood in the market. There are papers published describing these problems with this architecture. There's another problem. There are a lot of applications or use cases where it's important that there is no leader, that there's no opportunity for one party to control or influence what the community ultimately agrees on in terms of transaction order, or even prevent transactions from flowing into the community at all. For example, if we were building a distributed stock market, a matching platform, where we have bids and asks flowing into the platform, if it's possible for one party to prevent some of those transactions from making it into the platform, or to take certain bids or asks and change their order from what the actual order was, that's a bad problem. You can't trust the market. The leader can be bribed to do bad things, right? And it's not just stock markets, it's auctions or time-limited business transactions or games where multiple people are bending over to pick up a pot of gold. Which one of them actually pushed the button on the keyboard first makes a big difference. In all of those, you need fairness in the algorithm. Leader-based systems are not fair. The leader has too much power or control. That's the problem. So if we compare leader-based algorithms to public networks or proof-of-work blockchain, this is how that works. We have the miners here, each with their mining rigs. All of the transactions flow into the network. So every miner gets every transaction. If Alice wants to pay Bob a coin, that transaction, Alice creates the transaction, she submits it to the network, it goes to every miner. So every miner collects every transaction. The miners then take those transactions and put them into a block of transactions. And then they compete with one another to solve a hard crypto puzzle, the inverse hash. The miner that solves the puzzle first wins the privilege of taking their block of transactions and sending it to all the other miners with proof that they actually solved the puzzle. That's the proof of work. The miners validate the proof of work, and then they take the block and they put it on top of their local copy of the blockchain, the chain of blocks of transactions. So that's how that works. What are the problems? Well, one, proof of work is very expensive, and that's why these mining rigs are all connected to a power plant. That's to indicate how much electricity it uses. So it's very expensive. And in Bitcoin, I'd have to look at most recently, but it's on the order of $20 to $30 per transaction, US dollars per transaction. So it's really expensive. It's also really slow. Globally, Bitcoin can process approximately 5 transactions per second. Ethereum is maybe 15 transactions per second. Compared to leader-based systems, it's much worse. What about security? In this case, it's not possible to predict which miner is going to solve the proof of work or solve the crypto puzzle first. Because you can't predict, you can't do a DDoS attack. So it's DDoS resilient in that we don't know who to attack. So it's better than leader-based systems. And that's been the trade-off, is reducing security to improve performance on the permission side, better security, worse performance on the public side, and a lot more expensive as well. What about fairness? In this case, the miners, when they're collecting the transactions, they decide individually which transactions go into a block. They decide. If they choose to put a transaction in a block, they choose the order of the transactions within that block. It gets worse than that. If they see the transactions before they put them in the block, and so if they want to, they can create their own transactions and put them into the same block. And then if they win the competition, they publish their block and they've dictated the order of transactions, including their own, to the entire community. So it's not fair in the sense that I'm describing. So the market has responded by trying to solve this problem, the problem of proof of work blockchain. And specifically, what they're trying to do is eliminate the need for proof of work so that the cost per transaction will go down and the performance will go up. Oh, I'm in the front of this. Okay, thank you. Is that better? Yeah, thank you. we call this category economy-based. And the reason, and that's our term, we made that up. That's not a term that's understood in the industry. But we needed a category name. And so we call them economy-based solutions. And the way this works, each one of these nodes in the network, it's not mining rigs anymore. These are normal computers. The mining rigs are gone. That's the goal, anyway. Each one of these nodes in the network has an owner, an operator. If we make an assumption, a fundamental assumption, that the node operators are rational, that they will do what's in their own self-interest, meaning they're going to try to maximize the amount of money that they make. If we make that assumption, then we can put together a system of incentives such that when we apply that system of economic incentives to the community as a whole, the community, there will be an emergent behavior, specifically that the community collectively will decide which blocks to put on top of the chain and which blocks to prune or not put on top of the chain. Now, that's a little bit abstract. What's important is that all of these different variations have the same fundamental assumptions, that being that the node operators are rational. And Casper and IOTA and EOS and Tezos, they all use a variant of this type of thought. So what's the problem? First, this assumption of rationality doesn't really help. And here's why. Let's say this computer here is owned by Alice. So Alice is the node operator for that node. If I design a virus that is meant to infect Alice's computer here and then spend Alice's money to attack the network, to prevent the network to come to consensus, then it doesn't really matter if Alice is rational, right? That's not the right question to ask. The question that we want to be asking is, if a computer, a node, is infected by a virus, can we guarantee that the community will still come to consensus? That's what we care about. In fact, we want to make it stronger than that. We want proof that as long as fewer than a third of the nodes are infected by a virus and they're colluding to do bad things, it's still the case that the network will come to consensus. That's fundamentally what we care about. We don't care whether the node operators are rational and want to make money. That doesn't help us. There's another problem. This system of economic incentives, it's extremely complex, hard to formally analyze, let alone write math proofs like of what I just described. Right? Formally analyzing the system of incentives and then writing a math proof that guarantees the community will come to consensus, even with up to a third of the nodes being evil, is not possible. And it's not for the same reasons that real economies are hard to analyze or write math proofs about. If I were to ask you, if any of you were mathematicians, and I were to ask you, can you formally prove to me that the stock market will never crash again? Of course not. And why? Because it's a chaotic system, and it's hard to formally analyze it at all, let alone write a math proof. These are models of economies, and they have all the same problems as real economies. So what I'm saying is that we can't say anything objectively about the security of the network. It will be the case that an attacker will find a vulnerability. The protocol designers will find a solution to that. They will mitigate that attack, and then the attacker will find a way around that mitigation. And it will go back and forth. It's like an arms race that will just continue forever. what we have to do is fundamentally eliminate at the algorithm level the categories of attacks in the first place. That's what we want to do. How do we do that? If we go back 30 years, there is a category of distributed consensus that we call pure voting-based algorithms. And these work pretty simply as well. These are the computers. Each computer has a local copy of a database. And anytime a change is made by any computer to the database, that change or that transaction is sent to every other computer. It's a replicated database. So every computer has to receive every transaction. That's the minimum bandwidth required. Can't do any better than that. Well, we can set up a voting protocol where we ask each computer in the network to cast a vote on the order of transactions, a vote related to the order of transactions. And when we do that, every computer is asked the same question, and every computer sends their vote to every other computer in the network. And when a computer receives a vote, it sends an acknowledgement or a receipt, not just to the sender, but back to every other computer in the network. And then there may be multiple rounds of voting required to come to agreement on the order of transactions. As we continue to add computers, and we continue to increase the number of transactions, the bandwidth that's required just to process the voting grows exponentially. It's not practical. It's impossible to actually use this technology at scale. And for that reason, there are no pure voting-based algorithms in the market today at scale in the context that we're describing here. And so, why is this interesting? It's interesting because these pure voting-based algorithms achieve the best security that one can achieve. It's called asynchronous Byzantine fault tolerance, asynchronous BFT. And what asynchronous BFT means, practically, is that this category of algorithm is not susceptible to a whole class of distributed denial of service attacks, DDoS attacks. Any algorithm where there is a leader or a coordinator or the protocol depends on synchronous processes, it has timeouts in the protocol, those protocols are vulnerable to DDoS attacks. Asynchronous Byzantine fault tolerance algorithms are not. And for decades, people believed that asynchronous BFT at scale was impossible because nobody knows how to send the votes or do the voting without having to send the votes over the network. So how do we solve that problem? How do we achieve asynchronous BFT using a voting algorithm without ever having to send a vote over the network? That's what Hashgraph is. Hashgraph, Lehman, figured out in 2015 how to use a pure voting-based algorithm without ever sending votes over the network. And here's how it works. Remember, I said each one of these computers has a local database. It's a replicated database. Every change or every transaction has to go to every computer. That's the minimum bandwidth that is required. Let's assume this is Alice, and that's Bob. Alice and Bob. And so Alice has a message, a transaction, that she's going to pass to Bob. When she passes that transaction to Bob, Alice is going to add a little bit of information on top. Specifically, if Alice just now, talked to Ed, Ed passed Alice a transaction. Alice is going to take a hash of that message, a hash of that transaction. And then Alice just previously created her last message. She's going to take the hash of that one as well. 2 hashes. And when she sends this transaction to Bob, she's going to include with it those 2 hashes. a hash of the message she just previously received from somebody else, and a hash of the message she just previously created. And that's it. A couple of bytes. Three or 4 bytes maximally, and we can compress it to a couple of bytes. So it's a tiny amount of information on top. Every computer does the same thing. Every computer that has a transaction, when they send it to somebody else, they add those 2 hashes. We can take those hashes, each computer can take those hashes and build a data structure in memory that is the graph linking together those hashes that describes the flow of information across the network. This is the hash graph. It's a graph held together by these hashes. And the hashes the graph doesn't describe what the transactions are. The graph describes the gossip that is happening across the network. Specifically, who has talked to whom and when they talked to them. Who talked to who and when. Every computer has a local copy of the hash graph, and it's identical. They all have the same hash graph because we use cryptography to ensure that's the case. Now, when Alice wants to know what Bob would vote, if she were to ask Bob to cast a vote on the order of transactions using a voting algorithm, instead of asking Bob to send her his vote, she simply takes the voting algorithm, and there's enough information in this hash graph that she has in memory that she can calculate what Bob would vote if she were to ask the question. And she can calculate what every other computer would vote if she were to ask the question. And every computer has the same hash graph and uses the same voting algorithm, and they all can calculate what every other computer in the network would vote if they were asked the question, and they all get the same answers. They get identical answers. In other words, they're in consensus on the order of transactions without ever sending votes over the network. It's what we call virtual voting. So what does this mean? Like I said, this is a replicated database. Every transaction has to go to every computer. You cannot do any better than that. That's the minimum bandwidth required, period, for these types of systems. We add 2 hashes. I don't think you can do any better than that, ever. I think this is as efficient in terms of bandwidth usage as one can achieve. We've reached the limit of what one can achieve in bandwidth efficiency. Also, because we're using a pure voting-based algorithm, we've achieved the limit of security for the category. It is asynchronous, Byzantine, fault-tolerant. You can't do any better. In other words, I believe that Lehman has solved the problem of distributed consensus at scale. It may be the case that others come up with other solutions, but no one will ever come up with a solution that is significantly better than what Lehman has built. This is a solution to the problem as a category. So then the question is, what do you do with it? A fantastic piece of technology. What do you do with it? Well, there's an awful lot you can do. It can do everything that blockchain can do. And one thing I didn't mention is, in addition to being asynchronous BFT, it is fair. It's not possible for any single party to control the order of transactions that the community will ultimately agree upon. It's not possible for any single party to prevent a transaction from flowing into the network. It maintains the actual order that transactions are received by the network. So it's asynchronous BFT. It's provably fair, and there's a math proof associated with fairness property, and it's reached the limits of performance. So we can do a whole lot of things that you can't do otherwise. We can address games, We could do micropayments on graph, not micropayments with the Lightning Network or side chains, on graph. I say on graph, not on chain, for obvious reasons. Auctions, collaborative apps, Google Docs equivalent. We can do a whole bunch of things with this that you would never think of doing with blockchain. So what we've done, before we go here, what we started with were enterprise use cases. We started this in 2015. In late 2016, we competed with IBM and Hyperledger for the credit union business in North America. The credit union industry in North America decided they wanted a ledger to support arbitrary distributed applications for the 6,000 credit unions in North America, representing 105 million members. So we competed and we won. And we began to roll that out this year in January with the credit union industry. It's called CU Ledger, which stands for Credit Union Ledger. It's a credit union service organization. We then added a bunch of other enterprise customers throughout 2017 to our pipeline. We got to the point where we realized we had enough market validation and traction that we could begin to think about the next phase, that being a public ledger. We always knew we wanted to have a public ledger, but we didn't want to start where the rest of the industry starts. We didn't want to start with a white paper. We wanted to build the product first and harden it and make it enterprise grade. And when we did that, and we were comfortable that we had achieved that, then we decided it's time to think about a public ledger. So what about it? About 10 days ago, we were in New York City, and we had a big event at the PlayStation Theater on Broadway in Times Square. And, whoops, go back. Sorry. What Hedera is, we introduced Hedera, and Hedera is a public network built on the HashGraph platform, the same platform that our enterprise customers are using. And it's also a global council that's governing the platform and the associated cryptocurrency. When we were thinking about this, we were asking ourselves, what are the categories of problems that prevent public ledgers from going mainstream? Why is it that after years of availability, there are still no enterprise-grade applications running on any of the public ledgers? So we asked ourselves that question. We came up with 4 different problems that we thought we needed to address. One is performance. I think that there are just not that many applications that you can build on top of a ledger where they can only process 5 transactions per second. If we improve that to hundreds of thousands, then the range of applications that can be addressed is much broader. And the most interesting applications require this. Only the boring applications can be done with 5 transactions per second. And then security. If we believe that these platforms are going to process trillions of dollars of value, then we know they're going to be attacked. We know they're going to be targeted. And so we have to build security in from the ground up, meaning you have to start with the algorithm. You have to start with the best security at the algorithm level first. And then if you do that, the house that you build from this really solid brick looks very different than any other house that you've seen. So you have to start with the best security possible at the algorithm level. I'll skip governance and come back to it. Stability. The way in which this market has evolved has been both good and bad. Open source platforms have been fantastic in the innovation that they've unlocked, right? And there's been a lot of it, and it's been really good for the market. However, it's also the case that one thing we probably all agree on is that the main platforms, the most well used, the most prominent platforms, will probably split into competing platforms. You know, Bitcoin split twice last year. Ethereum is split. Others will go to market. They will get some usage, and they will split into competing platforms and associated cryptocurrencies. If I am an enterprise customer considering spending $2 million to build an application on a public platform, that worries me because I don't know what the platform is going to look like a year from now. So this is not the only problem, but a problem that needs to be addressed. In other words, we need to have open innovation, but with guaranteed stability. That's required by mainstream markets for enterprise use cases and mission-critical use cases. That's what we care about, right? If you can solve all of those problems, then the question is, what about governance? What's the right governance model to manage the platforms and the cryptocurrency? So we have answers to all of these problems. Of course, we've talked about the first two already. In terms of performance, HashGraph achieves hundreds of thousands of transactions per second. So in our white paper that we released just a week ago when we had our event in New York City, we have all of these results. You can take a look. There's enough information there that you can replicate the results for yourself. So we haven't hidden anything. We'll tell you exactly what we did. You can take the source, the SDK, and run the same experiments and get the results for yourself. When we had a test network across 8 different data centers around the globe, we did 50,000 transactions per second with consensus latency. That's the time it takes for the community to come to agreement on the order of transactions, with consensus latency of 2.9 seconds. And it's not probabilistic. You know, in blockchain, like Bitcoin blockchain, it takes about an hour to become pretty sure that that transaction is real. That coin that was just paid to the merchant, is it going to disappear? Well, that's not workable in most cases, right? When we do this, it's 2.9 seconds, not to 99.9% probability, but to 100% probability. It's guaranteed with a math proof, so it's not probabilistic. When we went from 50,000 transactions per second to 100,000 transactions per second, that consensus latency went from 2.9 seconds to 3.4 seconds. What Visa requires for their point of sale systems is 7 seconds. 7 seconds is their terms of service. And Visa, on average, processes about 2,000 transactions per second globally. And they surge to about 50. 50 is where we started. When we went to data centers in the United States, covering the coasts in Canada, what we saw was 250,000 transactions per second with 3-second consensus latency. It turns out that the algorithm is no longer the bottleneck, where it always has been previously. The algorithm is not the bottleneck. The bottleneck is new. If you have a transaction and you digitally sign it, if Alice is going to pay Bob a token, she creates the transaction, she uses her private key to sign that transaction, that's her signature. If I have 250,000 transactions flowing, I have to check 250,000 signatures. I have to verify 250,000 signatures. That's the new bottleneck, and that was a problem. So we had to solve that problem. We worked with one of the 2 global GPU manufacturers. In fact, they wrote a library for us to do signature verification on GPU in parallel. And so the question then was, can we do hundreds of thousands of signature verifications on GPU? You want to know the answer? It was 1 million. we could do 1 million signature verifications on the GPU. So that's no longer the bottleneck. So what does this mean? This means we believe we will be able to process hundreds of thousands of transactions per second, including cryptocurrency transactions. So we've solved the performance problem. What about security? As I've already mentioned, HashGraph is asynchronous BFT. That is the best you can do. You can't do any better. And it's got fairness associated with it as well. There's a proof of fairness. So we checked that box also. And one other thing, when you do this, at scale, this will be a sharded solution, meaning that there will be subnetworks all over the globe. Most of the time, when you go to a sharded solution, the system, the security of the system as a whole is degraded for some technical reasons. In our case, it's not. Because we're starting with asynchronous BFT, and we have a multi-sharded system with a messaging protocol in between, we maintain the level of security, not just within a single shard, but across the entire network as a whole. The whole thing is asynchronous BFT. Stability. This is where the patent comes in. So, we aren't going to require a license to use the public network. Anybody that wants to build an application on top of the public network can do so. In fact, if you're a developer, you don't even have to talk to us. You just use the APIs in the way that they're intended. So there's no license required. And if you develop the code, your code is your code. You can license that code however you want. Our software, our code, and our IP does not encumber yours in any way. It's your code. Also, we're going to take our source code, and with version 1 of the platform, we're going to put it on GitHub. Anybody that wants to look at it will be able to look at it. It's not open source, but it's open review. So there's full transparency in what we're building and how it works. You'll see it firsthand. You can take it, you can compile it, and compare it to the node software that you download to run a node on the network. And by the way, this is open consensus. Anybody that wants to run a node on the network will be able to do so. This is not a permissioned ledger. This is an open ledger. The patent is being used as a governance tool. What we can guarantee is that this platform will never split into a competing platform and cryptocurrency. We aren't going to allow that to happen legally. So we're making a promise to the market. This is the platform. It's a stable platform. You can build on top of it without worry. That's the promise. Okay, so we've solved the performance problems, the security problems. We've got innovation, open innovation with transparency in the source code and stability all at the same time. What about governance? When trying to think about what's the appropriate governance model, we realized what's important is that the mainstream markets, those developers of businesses and enterprises, etc., we need a governance model that causes them to trust us as an organization and trust us as a platform. And we thought back into history, what other organizations have had the same problems, needed to solve the same trust problems? What are those that can serve as a model for us? And we realized Visa did that. Back in the 60s, the founder of Visa, a guy named Dee Hock, had to solve the same kinds of governance problems. Specifically, there should be no opportunity for any single member of the network, the governing body, to have more or less control than any other member of the governing body. And so we used the Visa model as an inspiration. We used the same design principles that Dee Hock used in the 60s when designing our governance model. What that looks like is a council of 39 global enterprises. These are not a bunch of banks, although they do include a few banks. But these are organizations that have the most trusted brands by their geography and industry on a global basis. So there will be a few banks, there will be tech giants, there'll be insurance companies and telcos and transportation and retail and global consultancies. These are the biggest and best brands by sector, and they're geo-distributed. Now, these 39, what are they going to do? We're going to have subcommittees that manage every part of the business. So there is a subcommittee with oversight responsibility for the technical roadmap, a committee for legal, regulatory concerns, marketing and PR, finance, etc. We'll have a committee of some of the world's best economists helping us to decide on pricing of services and rates paid to the node operators. And yes, node operators do get paid in a way similar to Bitcoin, where Bitcoin you sort of win a lottery every once in a while. In this case, you get paid at a rate, an ongoing rate, right? But these 39 are providing governance of the organization. So it's a split governance model. It's open consensus, meaning anybody that wants to run a node in the network at scale will be able to do that. The 39 will also run a node in the network, and the first version of this will be run by the 39. In addition to the 39, we have another category of members that represent those companies or institutions that are important but don't sort of rise to the same level in terms of market cap. For example, Tsinghua University, Berkeley, blockchain at Berkeley, UT, University of Texas, as well as startups through multi-billion-dollar organizations are advisory members. They also will run nodes. So they're governing members and advisory members that will all be running nodes in the very first version of this platform. And at scale, at a multi-sharded system, anybody that wants to run a node will be able to do so. So it's open consensus with permissioned governance. So I think I've said this. Yes, I've gone through no license fee. This is important. And there are no notes. So what does it look like? What is the platform? Here's the internet. We have the HashGraph SDK that is the same SDK that we've been using for enterprise customers. On top of that, in version 1, we have 3 services. Cryptocurrency with support for micropayments, a distributed file storage system that's BFT, meaning that when you store a file in the system, you're given the proof that it's actually been stored. When you delete a file from the system, you're given proof it's actually been deleted. And the Ethereum virtual machine with direct support for Solidity contracts. This is not our implementation of a Solidity virtual machine. This is the Ethereum virtual machine directly on top of our platform. That's V1. We have a test network up and running today on 4 continents. And by the end of next month, April, we will be MVP, minimum viable product, with everything that you see here. We, 2 weeks ago, demonstrated internally running ERC20 tokens on the platform. So we have beta customers already ready to go. In fact, I'm going to let Edgar talk about some of those in a moment. And in about May timeframe, we will begin to add more beta customers building directly on top of the platform using this set of public APIs. Later this year, sometime before the end of the year, we expect to be GA, general availability for the platform.
Right. Can you hear me? Yeah, so we already have a series of applications that are planned for Hedera. So when at the launch event 10 days ago, Gabe Layden, who's the CEO of Machine Zone, it's a multi-billion-dollar gaming company. So they have games such as Mobile Strike, Game of War, Final Fantasy. And so he announced on stage with Manson Lehman the application that he plans to build on Hedera. In fact, if you watch the video of the launch event, he said he spent $100 million building a data center for this application. He's going to scrap all of that and move everything over to Hedera. We have Extreme Push, a company in ad tech, right? And that, with an application that processes 1 billion transactions per day, they're going to build an application on Hedera. Heartbit is another company. So they are, one of the co-founders is Matt Sorum, who's a drummer, who was the drummer for Guns N' Roses. His company is building an application to support up-and-coming artists and musicians. We have, last week, we announced that MindFund in Hong Kong, MindFund is a VC that launched the largest accelerator program for AI applications. They announced that they are launching an accelerator just to build applications on Hedera. So in addition to all that, we have other companies that have launched ICOs off of other platforms running into technical limitations that are approaching us to build their applications on Hedera as well. So you should be expecting a series of announcements related to all these applications that are coming up. So we're going to just open it up for any questions. But before we do that, I just want to highlight that there are certain things about token ownership that we can't talk about in a public setting. All I would say is that you can go to our website, hashgraph.com or HederaHashgraph.com, and there's a form where you can register your interest on how you want to participate in the community, whether you're a developer that wants to build applications, or you want to host a node, or other ways that you can participate in the community. So we'll open it up to any questions that you might have.
So using Hashgraph, it looks like you have a pretty good solution for making sure that everyone knows that the order that some messages occurred in. But based off of that, how can you build like a system of transactions where if I receive a transaction, I can validate that all the inputs are correct or something like that?
So the validation it depends on exactly what you mean, but I think I understand what you're asking. The application needs to do some validation. So let's just use an example. If it were a cryptocurrency application, who's going to validate the fact that Alice has the coins in her wallet in the first place to be able to pay them to Bob? That's done at the application layer. So in our case, for cryptocurrency, that would actually be done in the cryptocurrency service here. If you were doing transaction validation at the application layer above that, the application that's making these API calls, well, the application above that would understand the semantics of your transaction and would have to validate that the transaction makes sense in the context of the application itself.
So if you had like 400 nodes, then maybe 10 of them are running some cryptocurrency application. Would that be enough then to prove that, or to ensure some security in the transaction's validity? So
if we had a shard on the public network, every node in the shard is running the same set of services. So it would not be the case that within a single shard, you would have 10 nodes running the cryptocurrency service and 30 not. So every node is identical within a shard. And there are enough nodes placed randomly into shards that you can trust that there's not more than a third that are colluding to do bad things, meaning you can trust the order of transactions.
But then, how do you prevent civil attacks, as in, why can't I just join with 400 nodes?
Thank you for asking. No, this is good. That's exactly the right question to ask. That's part of the reason for the council. You have to bootstrap trust. You can't just start trusting let me say it this way. In a private network, you give permission to computers or nodes to join the network. And so in that context, it's not possible for one bad actor or a small group of bad actors to overwhelm the network with new nodes and dictate the order of transactions. The math says that as long as fewer than a third of the nodes are colluding, then you can trust the order of transactions. The community will come to consensus on the order of transactions. In a permission network, it's not possible for a bad actor to just stand up 1,000 computers and overwhelm the consensus protocol. In a public network, you have that problem. In a public network, it is possible for anybody that wants to actually stand up a node, and that node will vote in the consensus ordering. So it can't be one computer, one vote, because a bad actor, to your point, could stand up hundreds of nodes and dictate the order of transactions. This is where the cryptocurrency comes in. In our case, the cryptocurrency is the scarce resource. It makes it practically impossible for a bad actor to perform a Sybil attack, which is that type of attack where you overwhelm the system. It's no longer one computer, one vote. It's one coin, one vote. And so as long as not more than a third of the coins are, I should restate, as long as fewer than a third of the coins are held by a bad actor, then it's not possible to do a Sybil attack. But you can't start with just broad distribution of coins. So what we do is we start with the council of 39 and those advisory members as well, collectively holding 2/3 of the coins.
More than 2/3.
Actually, in this case, it's 2/3. As long as less than a third are evil, then you're okay. So if we hold 2/3, then we're good. Then we're good, right? Yes. I always get it backwards. I always get it wrong. But I think that's right. So the council will hold 2/3 of the coins in treasury, making it technically impossible for a Sybil attack to occur at all. Even if the entire coin pool that's floated into the market is owned by a single party, they can't do a Sybil attack. Now, we don't want to leave it there. That's just where we start. When the value of the coin increases and the coins that are in the market get broadly distributed enough, it will become clear that it's practically impossible for one or a few bad actors to own 1/3 of the coins. At that point, then Hedera will begin to divest treasury. The coins that are in treasury will be put into the market, floated into the market, until the entire treasury is floated into the market and the currency is totally commoditized. That's how you bootstrap this proof of stake system.
Thank you for the answer. I have another question too. So in terms of immutability, let's say that I post some very questionable content on maybe the Ethereum virtual machine. Is it possible for you guys to get rid of that, or are you just stuck?
No, it is. It is. So the way this works, with blockchain, you have a chain of blocks of transactions that goes all the way back to the very first block, the Genesis block. Hashgraph is a data structure that puts transactions in an order. But the application has separate from the hashgraph a state object. So if it were the cryptocurrency application, the state is the list of all the accounts and their balances. Now, they're not names on the accounts. They're serial numbers, the equivalent of serial numbers. Just random string of characters would represent an account and a balance. So that full list of accounts and balances is the state of the cryptocurrency. When transactions get put in order by Hashgraph, once they're in consensus order, they get applied to the state. And every node has a copy of the state object. Every node has a list of all the accounts and their balances. On a frequent basis, the community comes to consensus on what that state looks like at a moment in time. So you choose a moment in time, and then the community comes to consensus on what the state is. Once there's a community-signed state, a consensus on the state at a moment in time, then all of the hashgraph transactions that fed into that state up to that moment in time can be pruned from the hashgraph. The hashgraph doesn't grow without bound. You prune it. It stays small. You could throw them away. The state object reflects all of history. Now, if you wanted to change the state object, either by adding or deleting files, whatever it is, generally, then it's just a new transaction into the network. So you send another transaction into the network, and if it's talking about the file system, if this was questionable content, pictures or something that we as a society don't want to allow, then we can send transactions into the file system, and we can delete those, and we will get a proof back from the file system, because it's Byzantine, that they have in fact been deleted. So we don't have the same problems that other platforms have.
Thank you for the answer.
Sure.
Any other questions?
Hi. First of all, I wanted to thank all three of you for coming to Korea and explaining this awesome technology. I'm a fan, and I'll be continuing to see how you guys progress. I just have one question. It's about the governance council. So I think that's the main feature that's different from prior to 13th of March with your Hedera announcement. Before, you guys talked about all the other parts, but the governing council thing, that was a new thing that I thought it was very interesting. How do you figure out who gets to be in the council? What are the criteria? And I mean, you mentioned that they're established brands, but how do you define what an established brand is, and how do you know if you can trust them to make sure that they don't degenerate the ecosystem?
So listen, it's a great question. It's something we've wrestled with for quite a while. And so the idea is, it's a 39-member council. And what do you want to have this council do? You want them to individually be reputable, trusted brands that individually are viewed as unlikely to be a bad actor. So that's sort of point one, because their reputation is at such a level that they wouldn't want to jeopardize it. So that's sort of point one. Point two, we want to have as many sectors represented as possible. So we're trying to have 18 different sectors represented so that you don't have a likelihood of collusion. So that's sort of point two, broad sector distribution. Point three, geographic distribution. So we're trying to have every continent represented. Right now, we have people who've signed up from Australia, Asia, India, North America, as well as Europe. So, and we will continue kind of increasing that diversification. So those are the kind of principles in which we're working on. We're looking for brands that people know and that you all are very recognizable. The other point to mention here, which is critical, is that we're also cognizant that there's a bit of randomness. Whoever we find first, whoever finds us first, whoever gets to it first, and 39 from a global perspective is a pretty small number. We want it to be exclusive, but we also don't want, and so that's why we didn't want to make it 200, but we're limiting the opportunity to be on this council to a 3-year term, and each member is represented 2 consecutive 3-year terms. And so that's another way to ensure that if someone is a bad actor or even just doesn't do much, they may not get their term renewed. And so it's another way to kind of limit the risk with regard to the first set of members that we put on. And also to keep it clear, the council then is in charge of future members. So we are no longer in charge of the next generation of members. And members will turn over 1/3 every year. So there isn't even, the staggered membership, we think, further insulates it from unfortunate changes.
Hello, I have a question about data scalability. So we have three kind of scalability problems, like security and transactions, and also, as you know, the blockchain itself is not scalable, having all the transaction from the beginning and forever accumulating is not really a scalable solution. And I think some of your answer, you already answered some of that. And another question is about the security of a smart contract. As you know, that Ethereum smart contract is not secure at all. So if you, the smart contract that transfer the money is not secure, how are you going to guarantee the security of the full system?
Yeah. So I can tell you the approach that we take to the problem. So as you probably already see, we care a lot about having solid math from the very beginning. That's the reason Lehman spent 3 years beating his head against the wall to get to HashGraph. In addition to that, we have work ongoing and published already on our website using formal methods to prove the security of the algorithm itself. When that's completed, we will extend that then to use formal methods to prove the implementation of the algorithms. So we do use formal methods. That's basically writing math proofs and using a computer to check that the implementation of the software in fact matches the algorithm, which has been formally proven to have the properties. So we use math at every level and formal methods at every level. When it comes to the smart contracts themselves, the Ethereum virtual machine, it's interesting, the Ethereum virtual machine, when it was architected given the assumption that the network could only process about 15 transactions per second. And so that architecture is self-limiting. But we're including it there for backward compatibility. We are building another smart contract engine that will just run Java applications. So we're not making up a language, just use Java to write your smart contract and you'll be able to run that directly. So that is good and bad if you care about security and formally proving that the smart contract is secure. With Java, it's absolutely possible to build another language that is much more restricted, doesn't have the breadth of capability that Java has, because the smaller language, it's easier to make formal proofs about. And so it would be up to, as the market evolves and the platform evolves, we will continue adding different features. One of those very well may be a very limited language, but it would be written in Java that would run on the Java smart contract engine, and the language would be designed to be easy to write formal method proofs on. Does that help?
Yes, and do you have any have you ever considered using some kind of functional programming language for better formal proof?
That's a great question. I don't know the answer. That's a Lehman question. That's a Lehman question. I don't know if he has or not.
Okay, thank you very much.
Sure.
Then we can hear you. All right. No, not anymore.
Not anymore. Yeah. All right. Voting without voting sounds too good to be true, but I'll buy it. And thank you for the incredible technology. My question is about the governance. It's an extreme case, but I'll just throw it out there. Let's say just G20 countries, for some weird reason, decides to ban this, network.
Yes.
How do you,
What happens?
Yeah, what happens? Yeah.
Oh, I don't know. I don't know. I mean, so what I will say is that the governing members are not governments, right? We don't want to have governments involved in the council. So it's a non-governmental council, or made up of entities that are not governments. But if the G20, who knows? What I can say is that our approach has been very conservative, and we've taken steps at every point along the way to ensure that we should not be targeted by any government. If we are targeted by a government, then the entire market is in trouble, not just us.
Yeah, another thing I would add to that is we have been talking to governments that are planning applications on either Hashgraph in a private permission basis or on the public ledger. In fact, if GovTech, which is the technology arm of the Singapore government, published a blog post about 3-4 days ago about the application that they are testing out on Hashgraph. Any other questions?
There's one in the back.
Hello. I saw another presentation somewhere else mentioned that because of the math and security of your system, that it would be usable in a court of law. In the first time that I've heard about this pruning of past history, can you explain? That's not going to go back and
the pruning of the Hashgraph?
Yes.
So the state object, so two parts to the answer. The state object provably reflects the entire history. So whatever the state is today, it is that because every transaction in all of history has made it what it is today, and we can prove that. That's trivial to prove. It's also the case that there very likely will be a market for all of those transactions that got pruned. And so I would anticipate that some nodes wouldn't prune them. I mean, they may prune them technically, but when they prune them, they put them into persistent storage. You know, they put them on a hard drive, and then they offer them, as a product, if you will. So I could absolutely believe that will end up being, or maybe some charitable organization will keep all of history in terms of transactions and make them available. But it's not technically required for the protocol.
Would that be something maybe the council should be?
Yeah, I mean the council may do that. That's very possible. That's not. So I mean we aren't at the stage where we've considered that, but yeah, that's very possible.
Okay, one question.
Thank you for your lecture, and I thought that there are many differences between blockchain and hashgraph. The first one is that blockchain has only one hash value, but hashgraph has 2 hashes. And the second, the second difference is that in blockchain, like Bitcoin, we need a majority. I mean, 1/2 of the people should agree on the node. Then we adopt that node. But in hashgraph, you mentioned that
2/3.
Yes, 2/3. Why is that, and what is the difference between blockchain
It's
and
just
hashgraph?
it falls out of the math. And so, for example, with blockchain, if let's just say Bitcoin, for example, if Bitcoin were partitioned, the network were partitioned into 2 halves, then all of the miners on 1/2 would continue publishing blocks, and the community that sees those would continue to see blocks piling up on top of the blockchain on that half, and they would then begin to believe the transactions were permanent, and on the other half the same thing would happen, which is a problem. And so with ours, because of the way the technology works, it requires 2/3 of the total population to come to agreement. If the network were partitioned, and one partition was at least 1/3 or more, then transactions continue to flow, but the partitions individually don't come to consensus until such time that the partition goes away and they can continue to talk. So some people might argue that's a bug, others will argue that's a feature. I mean, if you don't want to have your dollar split into 2, or your coin split into 2 with a partition, then meaning that you're basically duplicating your wallet on both sides, which could be a problem, then you really want 2/3 of total population rather than 51% of a partition population.
Hi, thank you for your presentation. I really like your idea. So that's why I studied your consensus algorithm by myself. My quick question is that I think there is some censorship problem that might happen in hash graph. Let's suppose there are node A and B, and A send all in nodes to B, but B can choose not to pass on A's message to the other nodes. Is that possible scenario in
It's possible, but it's not sufficient. And it's not because of the way the gossip protocol works. So when A calls B and passes to B what A knows, you know, the difference between the two hash graphs, A doesn't stop there. At the next time, A calls somebody else in the population, and then at the next time, time 3, A calls somebody else in the population. So it's not like there's a single path that information flows through. It's more like a binary tree where the information is flowing to the entire population exponentially fast. So yes, one node could drop offline. I mean, it's not a censorship issue. It's an issue that you have to be resilient to, because nodes drop offline all the time. And so if Alice talks to Bob and tells Bob everything she knows, but then Bob drops offline before he passes on the information, you got to be resilient to that. And the resilience here is, as long as fewer than a third of those nodes drop offline, which is the equivalent of being malicious, then it still works.
I will have two questions. So let's get one here.
It's not my question. My tech-heavy friend asked me to ask you this question. In your testnet, how many nodes have you tested?
I think, well, so we've done several test nets. With AWS, we've done in the dozens of nodes, and all of that information is in the white paper. It's really interesting. This isn't just as an aside. We tried to test hundreds of nodes in AWS, and then even 1,000 nodes in AWS on a global basis. And even when working with AWS engineers, architects at Amazon, helping us with all of this, our system looks like a denial of service attack on Amazon. And so they shut us down. And so it's not been possible for us to test 1,000 nodes. That was what we've been wanting to do. We've literally worked for months with Amazon to try and get around this problem, but we've not been able to do the test that we care about because of their defense systems. We've also set up tests on Google. That's more recent. I don't have performance results from that. And with the test network, with the members that I described, that it's on 4 continents, I think we've got our first 11 or 12 nodes up and running.
Yeah, I think it's closer to 20 or 30 at this point.
Ah,
yeah.
He has the, okay, so we got 20 or 30 nodes on this.
Because my friend believes that more than 200 nodes, you know, he doesn't think it's possible. So, yeah, that's why he asked that question.
So, yeah, this is an important point. What we will have are nodes, some nodes that are highly performant, meaning that they've got a lot of CPU and storage and bandwidth, and then other nodes that don't. Those nodes that are highly performant will go into a high performance shard. And for those, we're going to get better performance than we would for low performance shards. There's another piece of this, and that is, how many nodes do you need or want in a single shard before you are secure, or before you feel like security is sufficient? So if you have a shard with 10,000 nodes, for example, that's probably overkill, because you could probably get away, assuming nodes are being assigned to shards randomly. When a computer wants to join the network, you assess its resources, and then you make a random assignment to a given shard. Assuming you're assigning nodes randomly, it's probably the case that a few hundred nodes within a shard is plenty of security. It's not very likely that a third of those nodes are going to be colluding. If you put too many nodes in a shard, you're wasting resources. you should have more shards because you can get better performance across the system as a whole. There will be applications that can take advantage of the fact that there are lots of shards and parallelize their work that results from that. So you don't want to have too many nodes in a shard because you're not optimal, but you want to have a sufficient number of nodes in the shard that you're secure. And so my guess is our shards, there probably won't be more than a couple hundred nodes per shard because that's very likely secure.
All right, well, I have one last question.
Thank you for the great presentation. And my question is that what is the advantages of HashGraph over a Lightning network?
It's more secure.
Next question.
Yeah, it's more secure. So in a Lightning network, you know, I understand the reason they're doing it. The reason they're doing it is because the chain itself is just not performant and it's expensive. And so it's a layer 2. We don't need layer 2. We just do it all on graph.
All right, well, thank you everyone for